Hello students, in this video we're going to work the first set of problems. This is on page 10 in the book, and this involves motion, acceleration, position, velocity, displacement, things like this. The first 5 of these problems are sort of conceptual problems. They don't so much involve those equations I was showing you at the end of the last lecture. They're just sort of, do you understand the concepts? And then the last ones actually ask for numerical answers. So I'm telling you what the answers are here, and of course the answers, you can find them also at the back of the book. I forget which page, it's like around page 190 or something like that. I agree with all of their answers in this case, and so I just want us to go through these problems and make sure that we understand how to do them. I've abbreviated what the problem statements are here. The first problem says that there's a weather balloon and the wind's blowing and it rises up 6 kilometers in the air. At the same time, the wind blows it 8 kilometers to the north and 10 kilometers to the east. And so they want to know what the final displacement is. Now, what displacement means is how far is it from its initial position. Now, if you know the what's called the distance formula, just chair out of the way. So if you know the distance formula, so this is number 1, for three-dimensional space, which of course we didn't talk about last time, and neither did it appear in the book up to this point, but if you do know the distance formula, then it would tell you that the displacement in this case is just the square root of the sum of the squares. So let me write this. So this would be the square root of 6 squared plus 8 squared plus 10 squared. This is like the Pythagorean theorem, except it's a three-dimensional thing. And so this would be the square root of 36 plus 64 plus 100. And of course, 36 plus 64 is 100 plus 100 is 200. So this is the square root of 200. Now, if I want to be cute, I can factor this into 100 times 2, and I can factor this into 10 squared times 2, and then I can bring the 10 out and get 10 square roots of 2. And if I write this in decimals, this is about 14.4, and then there's more decimals. And so the answer in the book is 14 is the one that's closest. It says approximately. What's the answer? And C is the answer choice. It says 14 kilometers. Now, if you don't know that algebraic distance formula, you could still figure out the problem by drawing a picture. And they have a picture of this in the back of the book. So you could draw a picture, and what you would draw is you draw like a box. And well, it's not really a box. It's a it's a rectangular solid, and so this represents the starting point for the balloon. And then now it's going to go 6 kilometers up, so I'm going to draw a 6 here. So that goes up from here to here. And then it's going to go 8 kilometers north. Now, of course, it doesn't go up first and then go north and then go east, but it amounts to the same thing. See, these are components of a vector in three-dimensional space. And so then it's going to go north. And so this distance here is 8 going north. And then it's going to go east. And so then this distance is 10 going east. Now, it's actually convenient for me to move my 8 and my 6 because I want to draw a little triangle here, 8 and 6. So what you could notice is that the distance along this diagonal, see, this is a box, and this is like the side, the left side of the box, and the distance along here is going to be 10y. Well, by the Pythagorean theorem, that's the square root of 6 squared plus 8 squared, which is the square root of 36 plus 64, which as we said is the square root of 100, which is the square root of 10 squared, which is 10. So that's this distance here. Now that relies on the fact that this angle here is a right angle. See, I have a right triangle here. This is a right triangle. The perspective drawing might make this a little bit hard to see what's going on. What's even a little bit harder to see is that if I then draw the diagonal inside the box, so this is going from this corner, inside here, under that line, and then up to there. So this is the diagonal from here to here. And this is really the displacement vector that we're interested in, because it's the one from the initial point up to the final point where it goes to. Well, we have another right triangle. In this case, what the right angle is it's the angle here. Now this is underneath there. It's this. So it has a side here of 10. That's this side here. And then it has a side here of 10. So this triangle is sort of floating there in space. It may be a little bit difficult to see, but you can see it if you sort of forget about the rest of the box. You could draw a right triangle that's sort of, and then this here, you imagine that's a right angle. This distance is 10, this distance is 10. And so this is the hypotenuse, and this is going to be the square root of 10 squared plus 10 squared. So anyway, you can rewind this and think about it more if you want to. I don't see why a problem like that would appear on, I don't see how something like that could appear on the MCAT, but you know, it doesn't hurt to know how to solve or how to visualize this sort of thing. So that's how to do that one. Okay, number 2. What number 2 is asking you is whether the Earth accelerates as it goes around the sun. And it asks you, well, it gives you some choices. Yeah, it says something to the effect where you could say, yes, it does accelerate because the velocity changes, or yes, it does accelerate because the speed changes, and then there's a couple of answers that are no, and some explanations for that. But it turns out that the correct answer is yes, the Earth does accelerate as it moves around the sun. And the reason why is because the velocity changes. So I'm going to draw a picture. So yes, it accelerates. And the reason is because the velocity changes. And so what the picture looks like is I have the sun here, and I have the Earth going around the sun. And I'm sort of treating it like it's a circular orbit. It's really not quite a circular orbit. It's more like an elliptical orbit. You may have seen these pictures, you know, the elliptical orbit, and that the sun is at one of the focal points of the ellipse here, and then there's the other one, and then there's the planet. We won't bother about all that. The answer would be the same in any case. Now, if I'm looking at the velocity of the Earth at a given time, the velocity is pointing in this direction because it's going, you know, that way. You know, if I was able to stand on the sun, I'm looking out at the Earth, I would say, well, it's going along in that direction. But the velocity doesn't stay the same. You know, when the Earth gets over here, it's moving in that direction. See, it's the vector is changing. Now, it's not changing much in magnitude. It does change a little bit in magnitude. It's a little bit closer to the sun at some points than others. And when it's closer to the sun, it's moving a little bit faster. But the main thing is that the direction of it's changing. So the idea is that the velocity changes. The magnitude doesn't change much. Magnitude is nearly constant. But the direction changes. It goes all the way around, 360 degrees. So direction changes a lot. So that's another one. There's nothing numerical about this problem. It's just a conceptual thing. Do you know what it means for something to accelerate? The idea is that the velocity changes. That's the essence of acceleration. It's a change in velocity. Okay, so that should do it for that one. The right answer, I believe, was D on there. And then number 3, it's asking about you take a trip like from one city to another or something, and it says, so here I forget what the cities are, but you have city A and then you have city B, and I think it says something to the effect that the airplane is flying from one to the other. It doesn't go in a straight line like this. It has a curved trajectory that goes like this. And so the question is, does the curved trajectory, now of course if you're going along the surface of the earth, if the cities are far apart, there will be considerable curvature just moving along the surface like that. But does the curved trajectory affect the displacement? And the answer is no. And this is just by the definition of displacement. So displacement, it means, so this is by definition, displacement means distance from initial position. It doesn't care a bit how you got there. I mean, so if this is point A here, I redraw point A, and point B over here, this is A, this is B. You could take any number of different paths from A to B, any way you want to go, like this. The displacement will be the same, because all it cares about, all displacement cares about, all that displacement can see is where did you end up versus where did you start. That's all it cares about. Now what is different is the distance along these paths. So I'll just write this up here. So note the distance, and that's different from the displacement. Now, like I said in the last video, this is something where it's like when you're doing physics, these words acquire new meanings that are more specific than the meanings that you're used to associating with them. A lot of people will use the word distance to mean just how far away are you. They won't necessarily care how long the path you took to get there is. So in this context, the way distance is used in this setting is to tell you how far you've gone along an entire path. It's like if you count the number of steps. So distance in this case means, and this is, we can't argue with it, it's just the way they're using the word. Distance means length of path that you've traveled. Whereas displacement means how far is the end point from the starting point. That's how the definitions are. And once again, there's no point in beating yourself over the head with it or thinking about, is that really right or is it really true? It's just how they're deciding to use the words. They mean, when you say displacement, I probably shouldn't have said distance here. I should have said, that makes it more confusing, doesn't it? How could I say it? See, that's why I don't really like using distance here. But I think I don't know why I put an S here either. Displacement means if you measure how far, I'll just say how far instead of distance. I'll just say how far, because there's no way how far could mean anything else. I think you get the idea. It's how far away you are, that's displacement, versus distance means, in this context, how many steps did you take along the path to get there? How long is the path? What's the length of path? That's the distinction here. Anyway, back to the answer. The answer is no. The curved trajectory makes no difference. It wouldn't matter if you flew in a bunch of circles or whatever. If you flew around the Earth the other way, the displacement would still be the same at the end. Okay. Number 4. Now, in number 4, what they do is they pose this problem where they say, okay, well, there's an interstate. Let me draw the picture sideways here because it'll be more, I'll have more room. So here's an interstate, and then there's this off-ramp. So you're getting off the interstate here. There's this off-ramp. And so here's your car. How do you draw a car from above? I'll just draw it like this. Your car is moving along, it goes off here. And then your car, of course, is slowing down as it's getting on the off-ramp here. So this is the interstate here, and so this is the off-ramp. And what the purpose of the problem is to compare the idea of velocity and acceleration, and in particular to make it clear that the acceleration and the velocity can point in different directions, and in this case they can point in opposite directions. See here, when you're on the interstate, you're going fast. You're going very fast. So this is large velocity. And then once you get off, you're going slow. So here's a slow velocity. I guess I will finish the word here too. Now, what that means, so when you're slowing down, if you're slowing down, if you're slowing down, it's like your seatbelt is pushing on you. So it's like you're being pulled forward in the seatbelt, or your seatbelt is pushing on you. Well, what way is your seatbelt pushing on you? It's pushing you back. It's pushing you back. That's the way in which you're accelerating. You're accelerating in the opposite direction of the way in which you're going when you're slowing down like this. So the whole point of this problem is that so when you have a small velocity, then the acceleration is going the opposite way. So you can think about the acceleration as that force that's pushing you back. It's coming from, when we do Newton's second law, that force equals mass times acceleration, you see that the force and the acceleration will be in the same direction. So that the fact you feel your seatbelt, pushing you back that way, that tells you your acceleration is in that direction. So the point of all this is that acceleration is in the opposite direction from velocity when you're slowing down. And that's all there is to that one. Okay, let's move on to number 5. Now, in number 5, they give you a list of descriptions that are supposedly describing a magnitude and a direction. And one of these descriptions doesn't describe a magnitude and a direction. And it turns out that the missing one, or the one that doesn't work, is the description of direction as in a circle. So this is the problem, that the phrase in a circle does not describe a direction. See, the other directions they were using that problem, like north or west or east or up or whatever, those are actual directions. In a circle isn't a direction. Remember when we were talking about the one with the sun, where we had the sun and then we had the earth moving around the sun? Well, it's moving in approximately a circular orbit, really more like an elliptical orbit. But I was telling you, well, the direction changes. It's not just one direction, it's different directions at different times. So in a circle is not a direction. It's a bunch of different directions at different times. So that would not be a magnitude and direction. So if I say something's moving in a circle, I am not giving a vector description. Now, it turns out that later when we talk about torque, or we talk about angular momentum or whatever, you can have something that's spinning around and there is a vector that's associated with that motion, but it's not a vector that's pointing along the circle. It's a vector that's pointing perpendicular to the circle. So anyway, that's the one that doesn't work. That's the black sheep there of those descriptions of vectors.